Hello again. We've wrapped up Appendix A, our algebra review, and we're moving on today with section 1.1 on linear equations and inequalities. And although we finished sort of the algebra review part, I still would expect for most of you that this chapter is partially review for algebra that you've done in the past. In fact, I know it should be because, for example, when solving quadratic equations, we did have to solve very simple linear equations there. So I've got quite a bit written up on the board behind me. Just very briefly, any equation that can be written in this form, so ax plus b equals 0, where a and b are just any real numbers you want, for example, something like 3x plus 1 equals 0. Any equation that can be written in that form, so not necessarily given in that form initially, but can be rearranged to look like this, where a is not 0, otherwise it's not very interesting. Any equation of this form is called a linear equation. And the way we solve linear equations is usually combining two different processes. You want to isolate x, and the way you do this is you add or subtract the same quantity from both sides. For example, first thing I would do here in solving this equation is I would subtract b from both sides. And then we can multiply and divide each side by the same non-zero quantity. So once I've subtracted b from both sides, to isolate x, I'd want to divide both sides by a, which I'm allowed to do because I'm told a is non-zero. So we'll do examples of solving these in a second, but we're also talking about linear inequalities. So I want to point out that if you don't have an equal sign here, if you have something like less than or equal to, or greater than or equal to, then it's no longer a linear equation, it's a linear inequality. Let's call it a linear inequality. And generally the way linear inequalities are solved is exactly the same as you do with linear equations. You go through these two processes, but I'll point out that there's one catch here with our second step, multiplying and dividing both sides by the same non-zero quantity. You have to be careful with inequalities. You have to be careful when you divide or multiply by a negative number. Because what that does is that actually reverses the sign. So for inequalities, reverse the sign. Or let's say reverse the inequality. I can't write. There we go. Reverse the inequality when multiplying or dividing. It's a little bit hard to write this low on the board. Multiplying or dividing by a negative. Right? Why is that? Well, suppose I have an inequality. Suppose I have something like 3 is less than 10. Absolutely true, right? But suppose I multiply both sides by minus 1. Is it true that minus 3 is less than minus 10? And the answer is no, right? Negative 10 is less than negative 3. So this is not true. When you multiply or divide by a negative number, the way you preserve the truthfulness of the statement is you reverse the inequality to keep it a true statement. So what we'll do, we'll start by solving several linear equations and linear inequalities, and then we'll talk a little bit about interval notation. Alright, so here's our first equation, our first example. We want to solve this equation. It's written as 3x minus 2 in brackets times 2x minus 5 is equal to 2 times brackets x plus 8 minus 8. So there's lots of different sort of orders you can go when you're solving equations. What I think is most natural here though is, and usually what you'd want to do when solving an equation that's written in a form like this, is simplify everything first. If you have brackets, if you have sort of things that need to be distributed, distribute everything out and simplify everything first. So let's do that. So let's see, this becomes 3x minus 2 times 2x, so minus 4x. And then minus 2 times minus 5, that becomes plus 10, is equal to 2 times x, so 2x, plus 2 times 8, so plus 16, minus 8. Okay, everything's distributed now, but once again, I can still group things together and simplify this, right? I've got 3x minus 4x is minus x. plus 10 is equal to 2x plus 16 minus 8 is plus 8. And now everything's simplified as much as I can. So our goal here is now to group all the x terms together. Anywhere I see x, I want them all to appear on one side of the equation. So what I'm going to do here is, let's see, I have a minus x here. I want that minus x to go away, so I'm going to add x to this side of the equation, because minus x plus x will make it disappear. And to keep it balanced, if I add x to this side, I better add x to this side as well, right? So we're going to add x to both sides of the equation, and that gives me now 0 plus 10, so 10 is equal to 3x plus 8. 2x plus x is 3x. Again, I want to isolate x, I want to get x by itself, so to get just 3x by itself, I need to subtract 8 from both sides. So let's do that. Let's subtract 8 from both sides of the equation. And that will give me 2. 10 minus 8 is 2, is equal to 3x plus 8 minus 8 is equal to 3x. Alright, so this clever sort of addition of the same quantity to both sides sort of allowed us to get x terms all by themselves on one side and all the constants all by themselves on the other side. And the only thing I need to do now is I want x by itself, so I better divide both sides by 3. So we'll just divide that by 3. That'll leave us with x, and divide that side by 3. So this gives me 2/3 is equal to x. And that's really all there is to it. I assume most of you are familiar with this process. You've taken courses in algebra before, so solving an equation like this wouldn't be a problem for you. And to be fair, this process of writing down exactly what I'm going to do, plus x to both sides, or minus 8 from both sides, or dividing both sides by 3, everything in red here, I'm not going to write that typically. We're just going to do this step mentally. The way I really think about this, and I think most people think about this, is instead of thinking of I'm going to add x to both sides, it's just I'm going to bring this minus x over. And you just change the sign as you bring it over. So minus x on this side becomes plus x on this side, so you end up with 3x. Similarly, this plus 8, I'm going to bring this plus 8 over, and it changes sign and becomes minus 8 on the left side. That's really how I mentally think about these things. One other thing you can do, I won't do this because it looks like it might be a little bit messy, but you can always verify your answer. If I'm claiming x equals 2/3 is the answer, then when I go back to the original equation, when I plug it in, it should be a true statement. I should get some number on the left is equal to the same number on the right. All right, here's our next equation. We want to solve this one. X plus 1 over 3 minus x over 4 is equal to 1 over 2, 1/2. So what do I want to do? Generally, if you have fractions, you want to get rid of them. Especially, in particular, if you've got something x over something, you want to get rid of fractions. So for example, what would I do here to get rid of this fraction, x plus 1 over 3? Well, I'd multiply both sides by 3, right? That would get rid of the 3 here. But then notice I've got x over 4. To get rid of that, I need to multiply both sides by 4. So how about we do this all in one go? I know I need to multiply both sides by 3, and I need to multiply both sides by 4, so that's equivalent to multiplying by 12. So let's just do that all in one go. We'll multiply both sides by 12 right off the bat. Okay? In other words, what I'm doing here is I'm multiplying both sides by the least common divisor of these two fractions, or least common multiple, if you want to put it that way. So yeah. All right, I've multiplied by 3 to get rid of this thing, and multiplied by 4 to get rid of this thing. Together it's 12. So we've got 12 over 3 is 4. That's 4 times x plus 1. Minus 12 over 4 is 3 times x, is equal to 12 times 1/2 is 6. And now this looks a whole lot like the equation we just did, the one we started with, The only difference is we started with fractions, we've cleared the fractions now, and now it looks like the equation we just worked with. So what do I want to do? I definitely want to distribute this out first. I want 4x plus 4 minus 3x equals 6. Probably want to group all the x's together now. In fact, I definitely want to. So 4x minus 3x is just x. That's x plus 4 equals 6. And the only thing I need to do now is isolate x. And the way I isolate x is I subtract 4 from both sides. So this 4 comes to the other side as a minus 4. And we're looking at x is equal to 6 minus 4, which is x equals 2. This one's a little bit easier to verify, I think. Let's plug it in. Let's see what happens. What happens if you plug in x equals 2 into this equation? Well, we end up with 2 plus 1 over 3 minus 2 over 4 is equal to 1/2. Is this true? Well, let's simplify this. 3 over 3 is 1 minus 1/2 is equal to 1/2. Great. That's definitely a true statement, right? 1 minus 1/2 is 1/2. Maybe I should have put the check mark here. So we have found the solution. This is exactly what a solution is. A solution is the value for x that makes this equation true, and the answer is the value is x equals 2. So I just want to point out, I mean, this is the whole point of doing this example, is pointing out that when you have fractions, you generally want to clear all of the fractions before you do anything. So I'd need to multiply both sides by 3, multiply both sides by 4. Well, together, that's multiplied by 12. Okay, so our next one is not a linear equation, it's a linear inequality, where we've got 3 times x minus 1 is less than or equal to 5 times x plus 2 minus 5. And if I put an equal sign here, you would know how to solve this. It looks like exactly like the two examples we've gone through already. And the less than or equal sign doesn't change much. You still use the same process, we just have to be careful, remembering that we have to be careful when we multiply or divide by a negative number. So what's our first step? Well, we distribute everything out. So we've got 3x minus 3 is less than or equal to 5x. 5 plus 2 is, or 5 times 2 is plus 10 minus 5. Let's just simplify that right-hand side really quickly. This is 3x minus 3 is less than or equal to 5x plus 5. Okay. Depending on the order I go here, I can avoid sort of having negative numbers, but I'm going to purposely introduce them so that we can see this process. So let's subtract 5x from both sides. Let's bring all the x's to the left-hand side. So 3x minus 5x is minus 2x. And we're going to do this all in one go. The minus 3 will bring that to the other side. Minus 3 becomes plus 3 because we're adding 3 to both sides. So plus 3 on this side, 5 plus 3 is 8. Alright, so we've got 3x minus 5x is minus 2x. And then 5 plus 3 is 8. Now what? Well, the last thing I want to do is to isolate x is I want to divide both sides by negative 2. And remember, if I'm dividing by a negative number, we reverse the inequality. So this less than sign becomes, or less than or equal to sign becomes greater than or equal to. 8 over minus 2 is negative 4. And there is our answer. And what I want to point out here is that there's certain notation that mathematicians use to indicate sort of exactly what's going on here. One way you can do this is you can plot this on a real number line. Right? So for example, here's 0, here's minus 4. If I'm saying x is bigger than or equal to minus 4 satisfies this equation, then I'm saying if you took 1 and plugged it in, the equation would be true. If you took 2 and plugged it in, the equation would be true. If you took 0, if you took minus 1, if you took anything bigger than negative 4, and including minus 4, the equation is true. So the way I'm going to indicate that is, well, I'm going to put a little square bracket here. I'm going to put a little square bracket here that indicates that minus 4 is a solution, because x can indeed be equal to minus 4, and so is everything bigger than minus 4. In fact, all the way out to infinity. So if you choose any number from minus 4 to infinity, that's a solution to this equation. Now, the last thing I want to point out here is this square bracket. This is usually called, what we're looking at here is an interval. This is an interval on the real number line that contains all the solutions. This square bracket is usually called a closed, it's the endpoint, and this represents a closed interval. Or closed endpoint if you want. Suppose I solved a different problem. Suppose we had the related problem of 3 times x minus 1 is strictly less than, so not less than or equal to, but less than 5 times x plus 2 minus 5. Well, you'd go through and you'd solve it in the exact same way, and the only thing that's going to change here is my solution would look like x is strictly bigger than minus 4. So a slightly different solution set. Every number bigger than minus 4 solves both of them, but negative 4 is a solution to this one. This one has to be strictly bigger, everything bigger than minus 4, so I can't include minus 4. And the way we represent this graphically is, once again, there's 0, there's minus 4. If I want to indicate that I'm not including minus 4, I'm going to put a little round bracket there instead. Okay, so instead of squaring it out, we make it round. And that indicates that I'm not going to include minus 4. And this is sometimes called an open interval, or the endpoints are open. And you'll see some questions in my math lab that ask you to sort of graphically indicate what your solution set looks like. And the last thing I want to say here is about notation in general. Mathematicians don't always like to draw pictures of the intervals. So we have notation for this. This is where the square bracket's coming in. This interval would be represented as square bracket, so minus 4. This indicates that I'm including minus 4 in my solution set, and we're going from minus 4 off to, all numbers, out to infinity. And traditionally, infinity always has a round bracket, because infinity is not really a number, we can't include it. So over here, this guy would look the same, but my interval, in interval notation, would be minus 4 to infinity with a round bracket on minus 4, right, as it is in the picture. So I'll make this very precise. I'll define interval notation right now, but graphically this is how we usually draw these things. So I'm not sure how good my explanation was that I gave you just now. So formally, here's the definition. This is interval notation. Instead of writing something like x can take on all values between a and b, so x is bigger than a but less than b, and graphically this would look like, okay, here's my real number line, here's a and b, and I want to allow x to be all values between them, but not necessarily, in fact definitely not including the two endpoints, so I'm going to use a round bracket there. So this is the interval, everything between a and b, and not including a and b itself. The way we'd write that in interval notation is just round brackets a to b. It means everything between a and b, and not including the endpoints. But if you want the very similar interval, where x is bigger than or equal to a and less than or equal to b, so very similar interval, the only difference here is it's everything between a and b and also including a and b. Then we use then we use square brackets. Square bracket a, comma, b, and then another square parenthesis. So square brackets means you include the endpoint, round brackets mean you don't. And you can also do similar things like this. You can have half open intervals, half closed intervals, where x is bigger than or equal to a, but less than or equal to b, So I put a round bracket on A and a square bracket on B. And once again, I'll point out that we have other things like A to infinity. This means that X is just strictly bigger than A. Infinity always has a round bracket on it because it's not a number, we can't include it. You can do other things like you can say minus infinity to B, and this means X is everything less than B, and so on. Right? And graphically, everything less than B, there's B, oops, good thing I caught this. I have a square bracket here, so this is everything less than or equal to B. So square bracket less than or equal to B, everything that lives over here in the real number line. Let's do another example. So quite often when you're solving linear inequalities, you end up with something like this where you have a double inequality. So I'm trying to solve this equation. I want minus 3 to be less than or equal to 4 minus 7x, but I also want that to be less than or strictly less than 18 at the same time. So how do you solve this? Well, the same way you always would. You just work with 3 different pieces of the equation instead of 2 different sides, as we were before. You just work with all 3 sides at the same time. So as always, I want to isolate x. What does that mean I want to do? Well, first thing I want to do is get rid of the constants. So how do I get rid of this positive 4? I want to subtract 4 from all 3 sides of the equation. So subtract 4 from all 3 sides. Minus 3 minus 4 is minus 7. When we subtract 4 from this part, 4 minus 7x, the 4 goes away. So we're left with minus 7x. And when we subtract 4 from 18, we have 14. Okay, so the equation becomes equivalent to this new one. Minus 7 is less than or equal to minus 7x is less than 14. And how do we isolate x now? Well, now I want to divide all 3 sides of the equation by negative 7. So we divide minus 7 over minus 7 is positive 1. Remember, I'm dividing by a negative, so dividing by a negative means I reverse the sign. Less than or equals to becomes bigger than or equals to, greater than or equals to. Is greater than or equal to divide by minus 7 becomes x. And divide 14 by minus 7 becomes minus 2. And once again, dividing by a negative means I flip the sign. This reads a little bit strangely to me. It's hard for me to read inequalities that point in this direction. So let's just rearrange this. What is this saying? This is saying x is strictly bigger than minus 2, and x is strictly less than or equal to positive 1. So if I were to plot this on a real number line, which is something the homework will often ask you to do, we're looking for everything between minus 2 and 1, not including minus 2, so strictly bigger than minus 2, so I'm going to put a round bracket there. But it does include positive 1, so I'll put a square bracket there. And this is our interval. So everything in this interval on the real number line is a solution to this double inequality. And if I were to write this in interval notation, this would just be minus 2 to 1 with a square bracket on 1. That's pretty much the whole section. The last thing I want to do is a couple of word problems. So using these skills, solving these inequalities, or just linear equations, but in a real world sort of application sense. Alright, so here's a sort of real world application of this stuff, and again, this is why math is developed, right? And most people don't do math just for fun. Math is developed to be able to apply to real world situations. So here's an example. Mary buys a new car. She pays 8.5% sales tax and a $190 flat title fee when she buys this car, and the total she ends up paying is $28,400. The question is, what was the actual purchase price of the car? Right, the total, after you include sales tax and the title fee, is $28,400, but what was the actual price of the car? So how are we going to solve this? Well, we need to set up an equation, and I'm going to have some sort of variable in this. I'm going to have an x in this somewhere. It's going to be a linear equation. And what you'd usually do is you'd say, well, I want x to be the unknown thing that I'm solving for. So what's the unknown here? Well, the unknown is the actual price of the car. So let's set this up. Let's say let x be the cost or the price of the car. And now I need to set up an equation. So I'm going to set up an equation. I want to figure out sort of all the different pieces that Mary paid. And what does she pay? Well, she pays the cost of the car. What else does she pay? She pays the sales tax. And she pays his title fee. And that's the sum of everything that she paid, right? Well, I know what that equals. I know that that happens to equal $28,400. So let me just write this as the total cost. We'll throw the numbers in the next line. So the total cost. So all three of those things together is the total cost of the car. Well, now let's replace these with our variables. The cost of the car, that's what we're calling x. So that's x. What about the sales tax? Well, the sales tax is 8.5%. But 8.5% of what? Of x, of the cost of the car, right? So the sales tax is 8.5% in decimal. That's 0.085 times the cost of the car times x. So this expression here, 0.085 times x, that represents the actual sales tax. And plus the title fee is a flat $190. That should all equal the total cost of the car, or the total cost of everything combined, is $28,400. So we'll go ahead now, we'll solve this very quickly. What do I want to do? I want to group all the x's together. I've got 1x plus 0.085x. That's 1.085x. Plus 190. Let's just subtract 190 from both sides right now. So this is going to equal 28,210. Subtracting 190 from both sides. And lastly, that means that x is 28,210 divided by 1.085. Not a very nice looking fraction. Now you would just pull out a calculator. I got that this is actually exactly equal to a nice number. This is $26,000. So that's exactly what you paid for the car. So how do we go about doing this? Well, again, you read the question and you see, what are you looking for? And the answer is, I want the purchase price of the car. So that's what I'm going to let my unknown be. I'm going to let x be the actual thing we're looking for, the cost of the car. And now I need to set up an equation. Well, what do I know? I know the total cost is $28,400. So I've got the total cost on one side. On the other, I want to write some other expression involving x that adds up to the total cost. So what do? Well, we just said our total cost should be all the different pieces. It's the cost of the car, plus the sales tax, plus the title. And that gave us this linear equation. And all we had to do then is solve the linear equation. We'll do one more. Okay, so we've got this sort of business question here, this business application. We're a company, this company is selling bike computers, and the question is, how many do they have to make and sell? How many bike computers do they have to make and sell just to break even? If the fixed costs, so setting up all the factories and everything, if the fixed costs are $36,000, the variable costs, each bike computer costs $10.40 each, and then they're sold to retailers for $15.20 each. So for a, what is that, $4.80 profit per computer. So let's just, again, let's let x be the thing we're trying to solve for. So what are we trying to figure out here? The question is, how many bike computers do we need to sell to break even? So let's let x be the number of bike computers sold. And it's important to be able to identify what you're looking for, what the unknown is, And the answer is we're looking for the number of bike computers we have to sell. So let X be the number of bike computers sold. And to break even, we need our cost to equal revenue. And that's when you break even, when your total costs equal the total revenue. So let's figure out what these things are. What is costs? Costs are going to be, well, it's going to be the fixed cost plus the variable costs, right? So fixed costs plus variable costs. So the fixed cost is just 36,000. Again, wherever that's coming from, setting up your factories, buying the warehouses or leasing the warehouses or whatever, there's our fixed costs. And the variable costs, well, every single computer costs us $10.40. Right, so the total variable cost is going to be 1040 times what? Times the number of bike computers we sell, right? So it's going to be 1040 times X. Not 1040, 10.4 times X. So there's our costs. What about the revenue? Well, each bike computer sells for $15.20 each, so our total revenue is just going to be $15.20 times the number of bike computers we sell, times X. Alright, so we break even when the costs are equal to the revenue. Alright, that's how we break even. We want these two things to be equal to each other. So we've set up an equation now. We've set up an equation and we're trying to solve, when does 36,000 plus 10.40x, when does that equal 15.20x? I don't have a whole lot of space on the board, but it doesn't look like a very difficult equation to solve. What do I want to do? I want to get all the x's on one side together, so let's subtract 10.4x from both sides. That's going to leave me with 36,000 is equal to 15.2 minus 10.4 is, what did I say that was, 4.8? 4.80x. I'll throw in the extra zero there even though it's not needed. And now if I want to solve for x, this means x is equal to, I'm just flipping the order that I'm writing this, I'll write the x on the left now. X is equal to 36,000 divided by 4.8. 36,000 divided by 4.8. And this comes out to exactly, if you plug this into a calculator, this is exactly 7,500. 7,500. So if you sell 7,500 bike computers, that's your break-even point. You want to sell at least that many to make a profit. And the process we went through here is the same thing. First, identify what am I solving for? What's the unknown? And what I'm solving for is the number of bike computers that we sell, so we'll call that x. And then you have to set up an equation based on the context of the problem, based on what you know, and I know that in order to break even, I need my cost and revenue to be equal. So we set up an equation for cost, which is fixed cost plus variable cost, and this can be written in terms of x. It's the fixed cost, 36,000, plus 10.4 times the number of computers you sell, so times x. And the revenue is 15.2 times the number of computers you sell, times x. And this gives you us a linear equation that isn't particularly hard to solve, and the solution is, as we found, 7,500. So we'll stop here. Thanks.